Hi guys, this is Mrs. Allison, and today what we're going to do is talk about comparison of series. So our goal is to look at two new tests that we can use to help determine if a series converges or diverges. Okay, so let's look at an example to start. Let's say we have a sub n, and that is equal to 1 over 2 to the n power. And then we have b sub n, which is equal to 1 over 2 to the n plus 1 power, or 2 to the n power plus 1. Let's write out the first 5 terms of each series. If we do that, if we plug in 1, so we see our lower bound is 1 for a sub n. If we plug in 1, we'd get 1 over 2 to the first power. And if we plug in 2, we would get 1 over 2 to the second power. Let's go ahead and just call that 4. The third term would be 1 over 8. The fourth term would be 1 over 16. And the fifth term would be 1 over 32. Okay, and we know if we went more terms, we would just keep going in that same pattern, but it only asks for 5. So let's do that again with b sub n. Again, starting with n equals 1. So in this time, we'd have 1 over 2 plus 1. So we'd have 1 over 3. And then we'd get 1 over 4 plus 1, so 1 over 5, plus 1/9, plus 1/17, plus 1/33. Okay, if we were to compare these two series, how would we say these values are related, or the series are related for all values of n? Hopefully what you would say is that a sub n is always greater than b sub n, or equal to. We may get to a place where it's equal to, but for n equals 1, it appears that it's always greater than. Actually, we could probably just say greater than in this case. Greater than. Why? Well, because I know 1/2 is bigger than 1/3, and I know 1/4 is bigger than 1/5, and 1/8 is bigger than 1/9, and you get the idea. So for each of those values of n, n 1, n being 2, n being 3, that a sub n is greater than b sub n. Now, we know a sub n is a geometric series. It fits that pattern of the geometric series where I could rewrite it as 1 over 2 to the n power. And so since we're finding the sum, let's find the sum of the entire series, not just the first 5. We would use that formula that we'd take our first term and divide it by 1 minus r. So in our case, it'd be 1/2 over 1 minus 1/2. That r value, remember, is the one that's attached to the exponent. So 1/2 divided by 1/2, we get that the sum of this series would be 1. Now, knowing what we know, knowing that the series a sub n is always greater than b sub n, and knowing that the sum of a sub n is 1, is there anything that we can say about b sub n? Remember, a sub n is always greater. What do you think you could guess from this or conclude from this? Hopefully you said something along the lines of that the sum for that b sub n series would have to be less than 1. The sum of something that has every term that's less than the a sub n series cannot be more than the a sub n series. Okay, now we know it has to be less than 1. Now, do we know if a sub n converges? We do know that a sub n converges. So if we can say that a sub n converges, and we know that the series of b sub n is less than the series of a sub n, since a sub n converges, what do we know? Well, therefore, we know that b sub n has to converge as well. Remember, we had that diagram, and we had that diagram that said if we have some graphs, and I don't know what they look like exactly, but let's call this one f of x, and let's call this one g of x, or a sub n and b sub n. If a sub n and b sub n, if a sub n is always greater than b sub n, we said that if anything less than that is going to converge if it converges. Now, if we knew b sub n was less than all values of a sub n and b sub n diverged, we could say the same thing about a sub n. But remember, if we have a series that's always bigger, then the series below it will always converge. Okay, that actually, we've just come up with the direct comparison test. So let's look at the direct comparison test. The direct comparison test says, suppose that we have two series that are positive terms, and for every situation, b sub n is greater than a sub n. That's backwards than the example we just did. Hindsight, I'd probably change that. But if b sub n is greater than a sub n, then if b sub n converges, then a sub n converges. Or if a sub n, the smaller one, diverges, then b sub n diverges. We've actually already looked at this. We're just putting it to a formal definition. So this is called the direct comparison test. So sometimes we may know what a series is and what it looks like. Sometimes we may have to make a comparison. There's several things that need to happen with that, and we'll go over that as we go. But let's look at these examples using the direct comparison test. Okay, so this first example says, determine whether the following series converge or diverge. So we're looking at the series from n equals 1 to infinity of 7 over the cube root of n. I may just rewrite this. Let's rewrite this as 7 times the sum from 1 to infinity of 1 over n to the 1/3. Why might I rewrite that? Do you recognize this type of series? Hopefully, you recognize this type of series. This series right here is what kind? This is a p-series. Notice it fits that p-series pattern. And in this case, our p is equal to 1/3. And the problem with that is 1/3 happens to be less than 1. And we know if p is greater than 1, it converges. But if p is less than 1, this series diverges. So really, if I multiply it by 7, which is always bigger than, we know it diverges. So we can say this diverges by the p-series test. Okay, let's look at another one. Well, this one is not as straightforward. This one doesn't fit any patterns that we've had before. But can I make a comparison? Can I compare this to, let's give it a series. Let's call this, let's look at 2 to the n over 3 to the n, which might otherwise be known as 2/3 to the n power. Do you agree that those are pretty similar? Okay, so your next question needs to be, what do I do, or how can I compare this series to this series? Which one's greater, which one's smaller? How do we tell? Well, if I'm adding 1 to the denominator, doesn't that make that number in the denominator bigger, which in turn makes the whole fraction smaller? Okay, so the first thing that we have to do is actually show a comparison. So what AP is going to want to see is they're going to want to see this comparison, that you know this is true. The next thing they're going to want to see is they're going to want to say, okay, what do we know about the series that I'm comparing it to? What do I know about this series 2/3 to the n power? Does it converge? Does it diverge? What? How do we know anything? Why did we choose this to compare it to? Well, I happen to know this is geometric. So I know this converges because it's geometric. And my R value in this case is 2/3, which is less than 1. And I know if my R value is less than 1, then it converges. And since the bigger function converges, what we know is that this series that we're actually focusing on, I may not know anything else about it, but because I compare it to something that I do know, and it's smaller everywhere, I know that this series happens to converge. It converges because I compared it directly to something I know also converges, and it's smaller than. All right. Hit pause and just see what you can do with C, maybe D too, but see if you can come up with an answer to these and just Try it. See if you can make a comparison or if there's another way you can determine whether the series converges or diverges. All right, let's look at this first one. Just like when we go to take limits and we look at some of these, sometimes it's easier to reduce the problem just a little bit to see if we can compare it to, or simplify the problem just a little bit. And if I look at the powers of these, I see that this is n to the first and n cubed. Now I know there's a -1 and I know there's a +3, but in the grand picture of all of this, the result of this is going to be something with 1 over n squared. So what I'm going to do is I'm going to compare this to 1 over n squared. Now, why would I choose something so simple? I choose this because I know whether this converges or diverges. I can use the p-series on this to determine convergence or divergence. Now I need to determine what the relationship is between the two. Which one is going to be greater than or less than all the time? Well, I know that this is going to be 1 over n squared is going to be greater than, oops, that's n cubed, n minus 1 over n cubed plus 3. If you don't feel comfortable with that, try a few values, if nothing else. Plug in some numbers. Like if we plug in 1 minus 1 is 0 in the numerator, that would be less than 1 over 1. If I plug in 2, I'd get 1 over 8 plus 3 is 11. Compare that to 1/4. I know that 1/11 is less than 1/4, and we could keep going. But that n cubed plus 3 is going to make that denominator quite a bit smaller. Or, sorry, the denominator bigger, which makes the whole fraction smaller. Okay, so because I know this, what I can say is I can say that the series that goes from 1 to infinity of 1 over n squared converges by the p-series test. Therefore, we know that the series from 1 to infinity of n minus 1 over n cubed plus 3 also converges because it's less than that series. Okay, so I'm not sure why it says p-series plus, p-series test I think is what I was about to write. We have to make these comparisons. We need to show that they're less than. We need to explain we know this converges, and then what result does that give us? All right, if you weren't confident enough to try those two before, hit pause now and see what you can do with part D. All right, let's make a comparison. The net result, if I were to think about this ratio here, if I were to think about the net result of this ratio, I might compare this to 1 over n. Sure, I could compare it to 4 over n because 8 over 2 reduces to 4. N squared over n cubed reduces to 1 over n. So I could compare it to 4 over n, but it's not necessary. We're really just looking for the most basic thing we can compare it to. Now, the tricky part is now, how do we figure out which one is greater than or less than if we're going to compare these two together? So if I compare these two functions, which one's greater than or less than? And again, if you need to, plug in numbers. If I plug in, it starts at 1, so let's plug in 1. The numerator would be 8 plus 1, which is 9, over 2 times 1 minus 1, which is 1. Great, I've got 9. If I plug in 1 over here, I get 1. Well, so far it's looking like the left-hand side is greater, that 8n squared plus 1 over 2n cubed minus 1. Let's try another one. Let's plug in 2. If I plug in 2, or 5, or 7, 2 is easier, I can do it in my head. 8 times 2 squared is 32, plus 1 is 33. 2 times 2 cubed, so 2 times 8 is 16 minus 1 is 15. And so that would be my second term. My second term over here would be 1/2. Well, which one's bigger and which one's smaller? Well, 33/15 is more than 1, so it is definitely bigger. So my comparison this time actually goes the other direction. Okay, so now I need to know what happens. What happens with the thing I chose? Well, we know that the series from 1 to infinity of 1 over n diverges by the p-series. This is also that one that we call a harmonic. Diverges by the p-series. And therefore, since my smaller function diverges, therefore everything greater than it diverges, which includes the function we just compared it to. Oops, that was a -1. Has to diverge as well. All right, let's move on to our second test. All right, the next type of test that we're going to look at is called the limit comparison test. So let's suppose that we have two series again, a sub n and the series of b sub n, and they're both series with positive terms. What we can do here is if we take the limit as n approaches infinity of the ratio of the two functions, the a sub n and the b sub n, and they equal some number. Do you remember what this means? Do you remember what it means when we take the division of two things, we compare two functions, and their limit equals a number? Do you remember that this means their relative growth rate is the same? And more than that, let me finish writing this. Relative growth rate is the same. When we get their relative growth rate is the same, then whatever we're comparing it to, the series that we're comparing it to, if the series we're comparing it to converges, then they both converge if we get that L. Or if we get that L and the series we're comparing it to diverges, then the one we're looking at also diverges, okay? And what this test is good for is this is a great tool to be able to compare really messy algebraic series with something simple like a p-series. So what we have to be careful of is that when we are choosing a comparison series, that we choose a p-series. P-series is the easiest to choose, that has the same magnitude as the function we're choosing. So for example, if we want to see what happens to this series, then I'm going to choose a p-series 1 over n squared. I'm going to choose this because n squared, this one has n squared as well. So I can make that comparison. Okay, so the point of the limit comparison test, we're going to compare the limit as n approaches infinity of the ratio of the two series, the functions of the two series, and if we get L, then we know they either both converge or they either both diverge. And it all depends on whether the one we chose, again, should be a p-series, converges or diverges. So let's look at an example. This first example says that we're going to take the sum from n equals 1 to infinity of 2 over n cubed plus 4. Now, this is not too messy of a problem, and I could do a direct comparison here, but I'm going to show you what the limit comparison looks like. So let's compare this one to, let's do the series from n equals 1 to infinity of 1 over n cubed. We know about that one. Tell me what we know about this series. Well, we know this series right here converges. Why? We know it converges because of the p-series test. Because the p-value is greater than 1. So we know that converges. Okay, so what we're going to do is we're going to set up the limit as n approaches infinity of, and I'm going to take, and it doesn't matter which order you put this in, so I'm going to take the more messy function and divide it by the one I'm comparing it to, the 1 over n cubed. Now I can't leave it like this, so I'm going to do some work with it. So I'm going to rewrite this as the limit as n approaches infinity of, this would be 2n cubed over n cubed plus 4. Now, certainly if I were to substitute in infinity right now, we'd get infinity over infinity, which would be a L'Hopital's rule. However, if I use the derivative at this point, I'm going to end up taking the derivative multiple times, and in the end, what I'm going to get is a ratio of the leading coefficients. So this we can look at here and notice that they both have the same powers at this point. And so this limit happens to be 2. And what that means is the two functions that we started with, this 2 over n cubed plus 4 and the 1 over n cubed, have the same relative growth rate. And therefore, since this function converges, we can say that the one we're looking at also converges. So this is the limit comparison test. And the limit comparison test says we're going to compare it to a p-series that we know either converges or diverges. And then I'm going to take the limit of the ratio of the two functions. And if I get a value, then I know it converges if the original one converges. If I get a value and the original one diverges, then this one diverges. So hit pause and try the next one. All right, let's look at this one. Hopefully when you look at this one, the first thing you notice is just a way to make it a little bit simpler. So if we look at the numerator and the denominator, the highest degree, really what we have is n to the fourth over 4n to the fifth, meaning what we really have is 1 over 4n. Okay, so if you were to think about a p-series that we could compare this to, hopefully you would think about comparing this to the series that goes from 1 to infinity of 1 over n. And tell me what we know about this one. Does it converge or diverge? Well, this diverges. So now we need to see what happens here. I'm going to take the limit as n approaches infinity of that lovely function right there. N to the fourth plus 5 over 4n to the fifth minus 2n cubed plus 3 all over 1 over n. And I'm going to do some simplifying before I go on. This would be the limit as n approaches infinity. And this would give me n to the fifth plus 5n over 4n to the fifth minus 2n cubed plus 3. Now, if we look at this and I take this limit is really just 1/4. Using that relative growth rate of each of those, this would be 1/4, which means that 1 over n and this function have the same n behavior. They're growing at the relatively the same rate. And so therefore, since we know the 1 over n diverges and we got an actual limit value, what we can say then is this series from 1 to infinity of n to the fourth plus 5 all over 4n to the fifth minus 2n cubed plus 3 diverges. So since the one diverges, the other diverges because we got a limit that was a value. So that's our limit comparison test. So now we've got several things that we've talked about. We've looked at the limit comparison test, the direct comparison test. We've talked about geometric series and p-series. We've also looked at the integral test and the nth term test. So we've got a lot of tests that we can use to determine convergence and divergence. So hopefully that helps, and with the idea of comparison of series, and we will continue our discussion on alternating series next.